This is the first video of many videos and a tutorial on how to do non-targeted analysis for PFAS. In this video, we're going to discuss what PFAS are and why we need this special method called non-targeted analysis using mass spectrometry to be able to detect all of the PFAS chemicals in our environment. In this introduction, I'll cover a little bit about the environmental source and fate of PFAS and what they are chemically, but I will not cover deeply about the health effects of PFAS. For that, we can see a separate tutorial video. There have been large epidemiological studies showing that these chemicals are linked to cancer, especially testicular cancer and other cancers. There also is research on them as endocrine disruptors, as obesogens causing obesity, as well as many other health effects such as immune suppression. But again, that can be a topic for another time. So PFAS are these chemicals that usually have this long carbon-fluorine chain, and they're fluorinated organic molecules. Now, this is a periodic table that shows each atom and their electronegativity. If you remember, the differences between electronegativity causes stronger bonds, especially if they still form covalent bonds. So carbon, the most electronegative atom on the periodic table, is fluorine at 4.2. And so carbon at 2.5 will form the strongest bond with fluorine out of any atom on the periodic table. Now, why are we talking about this? This is what gives PFAS some of its very unique properties. One is that it has a very strong carbon-fluorine bond, so it's very hard to break apart. This is good for a lot of the products it's used in. It can be used in high heat situations as lubricant. It can be even used in jet fuel and other high-end industrial processes or products where you need to have a very strong, stable chemical. Two, it looks very different than other molecules. So if you replace those fluorines with hydrogens, and we'll talk about those two comparisons throughout the tutorial, you get a fatty acid. Looks exactly the same, but has hydrogens instead of fluorine. That fatty acid and most other molecules that have carbon-hydrogen chains are lipophilic, meaning that they're oils or oily and they attract to other oils and they dissolve in other oils. And they're nonpolar and they dissolve in other nonpolar materials. Then you can also have molecules such as water, which are very polar and dissolve in polar molecules. What if you wanted a food packaging that repels both oils and water, neither suck into them? That can be very difficult. But PFAS are very unique. Because light dissolves light, they don't look anything like anything in nature. There's no carbon-fluorine species found in the natural environment that we've detected that I know of, and it's definitely not abundant in the environment. And so all of the PFAS that we measure are anthropogenically or man-made, anthropogenically sourced or man-made. And they don't look like anything in nature, so they repel water and oil. So they can be used in rain jackets, food packaging. They're great in lubricants because of their ability to not break down, and still they have lubricant-like properties. They have many, many uses. What defines a PFAS? So PFAS, like I said, have carbon fluorines, but depending on the organization, the country, the regulatory agency that's involved, they can have very different definitions. I like the definition given by the EPA on their Comtox chemicals dashboard when they pool and make a giant list of PFAS out of all the chemicals they have there. They make a very simple definition that a PFAS is something that has 30% or more fluorine by atoms, excluding hydrogen. So if it's a CO2 CF3H2, for example, I'm just making something up, this would likely be a PFAS, because if you divided the 3 fluorines by the rest of the atom, you get over 30%. So this is a very simple definition and easy to execute and understand. There's other definitions as well. So the original one on the EPA CompTox dashboard was a substructure-based one, where it said, hey, if it has a CF2 chain of at least 2 units, or a CF2 chain separated by a CH2 chain, or a CF2 chain separated by a fluorine and a hydrogen, or, as you can see as we walk down the line, ether linkage with 2 CF2s on either side, and so on and so forth. If it was any of these 5, contained any of these 5 substructures, then it was considered a PFAS. Of course, they've updated their definition to the 30% fluorine. The OECD says that it has to contain at least 1 saturated CF2 or CF3 part of the molecule. And then there's other, you could call it, definitions of terms of PFAS in terms of regulation. What's regulated as a PFAS might be different than what would structurally be considered a PFAS. Now, as far as PFAS production, PFAS was originally discovered in 1938 by accident as Teflon, which is just this CF2 chain. And it's extremely strong. Again, water and oil repellent. And so it can be used in a lot of products, and it was used in the Manhattan Project for the development of the atomic bomb. So that was its first major use. Then, in the 1950s, the story that I understood is that Teflon, the wife of one of the people who was using Teflon or invented Teflon, she saw the product that he had brought home, and she tried it on her pan. She said, hey, why don't you try this? Bring it home. I'll try it on the pan. And her eggs no longer stick to the pan, and they wouldn't burn to the pan. And they said, well, let's start creating these non-stick pans using Teflon. And so that's where the first non-stick pans came from. And that was its main use. 1960s, about 10 years later, they started being used in firefighting foams. They worked extremely well in extinguishing fires and still are one of the most used firefighting foams, which very high concentration of PFAS, as with the pans. And then 1970s and onwards, there was a significant expansion of the use of PFAS in industry. So the chemical industry found in all kinds of other uses, whether it's the coating on a kayak or on a rain jacket or in Post-its notes or so on and so forth. There were a lot of uses of PFAS. Scotchgard carpets are one of the major sources in homes. And so this is just a picture showing that, for so many use cases, they wanted different chemistry, so they created so many different chemicals. Here you can see, and we'll talk about this as well throughout this tutorial, is that a PFAS consists of a subclass. We won't go deep into subclasses now, but a subclass is defined, for example, as the units you see in all these structures that are not the carbon-fluorine chain. And then the carbon-fluorine chain, in this case, is denoted by A, and then the CF2, and then A, and then F, meaning that this is a repeating CF2 chain that can be extremely long or short, usually ranging from just a single CF3 unit to 10 CF2 units, but have been measured above 20 CF2 units as well. Here are some other use cases for PFAS, and again, it's used in so many products, makes it hard to avoid, and as we mentioned, it doesn't break down, right? It's very strong. We said that's good for it as in products, but it's also bad for it in the environment. And so in your home, you can found in all your water, so you can absorb it when taking a shower. You can drink it in your drinking water. You can inhale it from indoor dust from the home. It's actually directly in, and probably the major source is in your carpets if they're Coated carpets with PFAS or treated with PFAS to be non-stick can be found in your paints, cleaning products. Some things have it not intentionally added, but because of the lubricants or other industrial processes, such as toilet paper, it may not be intentionally added, but there's PFAS in a lot of paper products accidentally, and then a lot of fast food packaging, it may be added intentionally, as well as compostable materials, so that those don't dissolve or stick, have oil soak in or water soak in. Again, here are some of those structures. The two most common PFAS are ones that end in a carboxylic acid. Here on top, highlighted as a square in the square. That's carboxylic acid, again with different lengths of carbon fluorine. On the bottom is sulfonic acid with different lengths of carbon fluorine. Originally C8 and still C8 for both these species, which means 8 carbon fluorine chains is the dominant one for both sulfonic and carboxylic acid species. So these are the most dominant PFAS, the most well-studied PFAS, the ones we know about health effects, etc. A lot of animal studies, fate and transport properties, remediation often tracks these, measurement methods track these, and yet there's so many more PFAS to be discovered and identified. So PFAS stands for perfluoroalkyl substances. So and it can also be per and polyfluoroalkyl substances. And we won't go too much, but again, here's your sulfonic acid on the bottom and your carboxylic acid on the bottom, and then you have this chain of carbon fluorines. Now, talk about the sources, transport, and fate of PFAS. So I talk about consumer products, a lot of consumer products, aqueous firefighting foam, a lot of different sources. So here's a picture of, a human society, and we can zoom in on different portions of this to see how PFAS moves through the environment. So one is through firefighting foam. And so airports, military sites, other sites where there may be major explosions or there's major fuel storage, all of these have to have a lot of firefighting foam on site, and those can spill, but they can also use them in the case of their fires. And anytime there is a fire, and they put out fires with firefighting foam, so when there's large wildfires, for example, and they're using firefighting foam in certain cases, that will lead to major PFAS contamination. So for example, in Japan, one of the major sources of PFAS, sadly, is not from Japanese industries, but from U.S. military sites. A landfill is another source of PFAS, and John Bowden is one of the leaders in the field, as well as Timothy Townsend, looking at PFAS in landfills. And they're both at the University of Florida, so I'll show a little bit about their work. But landfills, all of our consumer products, etc., goes into landfills. And then the landfill leaches and creates leachate, so this water that comes off the landfills. Also, there's gas that comes off the landfills, whether it's burned or not. And all these can be sources of PFAS. Often, there'll be remediation of water that comes off of landfills, meaning that they'll clean up some of the organic matter, contaminants, the bacteria from waste such as feces, etc. And this can also be from sewage. But they do not clean for PFAS, and because PFAS is not like many other molecular species, they can often escape these cleaning processes and get back into the water that we drink. So here's an example of a project that was done in John Bowden's lab, and just kind of showing a fun video of them collecting transfer station leachate. So maybe not a job you want to do, but this would be very high in PFAS. This is another work by John Bowden, and this is looking at the distribution of PFAS in Florida And there's the predicted total PFAS based on their measurements. Over 1,000 measurements they took throughout Florida, measuring many different PFAS. And then they found that there was about 1 billion gallons of sewage spilled accidentally in Florida, maybe from hurricanes. I know there's digging sometimes breaks a line, so on and so forth. So there was a lot of spills. And if we look at some of these major spills, they actually correlate very closely to the PFAS concentrations. So while correlation isn't causation, this infers that at least in Florida, one of the major sources of PFAS in the environment, at least, is from these sewage spills. Now, this is getting into a question of why non-targeted PFAS. And we haven't discussed what targeted and non-targeted is, but very briefly, and then we'll go into more detail, explanation is targeted is you know what you're looking for specific PFAS, and non-targeted means you're looking for everything, including unknown PFAS. And targeted, you're looking for a narrower range of PFAS, only those that you know exist and that you can synthesize and have known chemicals for, and non-targeted, you can use universal principles for and discover a much wider net of PFAS. So, this is one reason why non-targeted PFAS would be very important, is because if we look at a screening method that was targeted that had 52 PFAS, and that's quite large for a targeted method. So they had 52 known chemical PFAS they were looking for, and that's in black over here. And you can see this is the percent of the total PFAS that was in this sample that was covered by those 52 PFAS. And in most or every case, that was less than 10%, or often even less than 1% of the PFAS were those that they were looking for. And they know this because there are methods out there where you can get extracted organic fluorine, you can get anionic and neutral organic fluorine. So there's an analysis where you can get these you can also get total fluorines. And so we know what the concentration of organic fluorines, even if we don't know what they are in the sample, and then we try to fill that gap. So again, many PFAS that may or may not be discovered if we're only using targeted approaches. We're missing a lot, and all of these might have health effects. They might have different properties in the environment. They might be much more concentrated than the ones we're looking for. So this is a very dangerous situation because we have no eyes on the ground. We can't see what the PFAS are. How are we going to regulate them? How are we going to know what their health effects are? How are we going to know if an industry starts to dump them? And so it's very important to be able to detect them. We can also see the same thing for public drinking water. So again, this water is going to come from the environment. Often it's not treated for PFAS, and so PFAS gets into the drinking water. This may not be one of the major sources of PFAS. Dust, for example, has way higher levels. Some products that we have in our house have way higher levels, food packaging. But it is a source. And one of the sources into water is direct discharge. Surprisingly, some manufacturing industries treat and some have less treatment, but a lot of PFAS still comes out of their discharge into water bodies. And the Environmental Protection Agency is working on detecting those and making sure that this does not happen. So I work with Jackie, Mark Striner, and James McCord at the Environmental Protection Agency. And using the software that we'll be discussing as part of this tutorial, we'll use it as an example of how you would go through data. We were able to identify thousands, and by that I mean Jackie Bangma and Mark Schreiner were able to identify thousands of PFAS in these industrial effluent samples or before and after treatment from different major manufacturers. And then they were able to put those back into the libraries of our software so that we can detect them with high confidence in the future. So in non-targeted analysis, we can go completely unknown using universal principles, which we'll talk about in depth, but we can also have libraries or rules we get from structures we do know something about and then screen for those in future samples, which makes the job a lot easier. we're going to continue this work with Rachel Smolinski and Parker Chang to now add collision cross-sections as well. So what about human blood? Okay, it's great. There's a bunch of PFAS in wastewater. There's a bunch of PFAS maybe in my rug, but am I being exposed and is it in my body? Yes. Way over 90%, 98% in most studies of humans have PFAS in their blood, detectable PFAS. Not only that, but often relatively high levels of PFAS as it concentrates in the blood. Because again, it does not stick to water, it does not stick to oil. It's neither polar or nonpolar in that way. So it actually sticks to the proteins in the blood. And so as it's on the proteins, it concentrates in the blood, where the bloods have lots of proteins in them, the albumin. And so we can measure the PFAS in the blood over time. Now the good thing is, and we haven't covered this talk, that would be a separate tutorial, is that since 2001, there has been a drastic decrease in some of those major PFAS, so PFOS and PFOA that we discussed earlier, the carboxylic acids and the sulfonic acids, specifically C8. But also a number of the other species have also decreased. And that was because of scientific research, discovering these species, of scientific activism, of legal activism. A lawyer really stood up, and there's a great movie called Dark Waters and Devil We Know that go into the issue of PFAS and how this one lawyer really worked to change this field, of course with many other people as well. And so this is one of those examples where change can happen. The issue is, there's a but here, and this is where non-target analysis is needed, is that while the total PFAS from these targeted methods was decreasing, the actual PFAS measured by extractable organic fluorine, so all of that, even if we don't know what they are, is not decreasing since 2001. And what this means is that there's a bunch of new PFAS being manufactured that we're not aware of to replace the old ones. And so that's why, and we're not seeing them, but so that we're still being exposed to the same amount of PFAS, it's just different structures. So we have to know what these are. In summary, unknown PFAS must be increasing in serum. What are these PFAS? How much are there? How toxic? We need non-target mass spectrometry, and we need software. And that's what we're going to discuss throughout this tutorial, is the methods that we can use to close this gap, to identify these PFAS that are unknown. So fluorine analysis, especially total organic fluorine, again, can give you the total picture of how many PFAS. And then non-targeted analysis, even though we're using universal principles, it's important to note before we get into it that not everything will be detected by the instrument. And so even if we're able to identify everything in our data, which is quite a challenging task, we still won't identify all PFAS in the sample, but we will cover way more than previously detected. And then, of course, there's targeted analysis, which covers the smallest section. Here's another study, again, just to take this message home. This is on a bunch of surface waters and water systems, and publications below, and showing that, again, in these water systems, the targeted PFAS that you get from a targeted method, and these are the main methods used by most research labs, is not covering enough PFAS. We need non-targeted analysis. So the advantages of targeted, though, are they're easy to, or relatively easy, relatively less expensive. Still expensive, still challenging. You still need techs and people who know a lot about what they're doing there. The annotations you get are very confident. You can use a known chemical standard, a known PFOS, for example, put it on your instrument. You know exactly all the different evidence that we'll be discussing later on. You'll know exactly how that evidence should look, and you can confidently assign a structure. It's also much faster in terms of you don't have to discover anything. You already know what you're looking for. As soon as it appears, you can detect it. It's reproducible. You're actually getting units in concentration. So, for example, parts per million. And that quantitative answer is very important, right? Because we want to know it's not whether PFAS is in your blood or not, it's how much. And if it hits a certain threshold, it might be toxic, whereas below that threshold, the effects might be minimal. So we really want to know how much, and then we can compare between labs because we actually have a known value. It's hypothesis driven, so we have a question about certain molecules that we expect to change, and then we'd be looking at those molecules. On the other hand, there's non-targeted analysis, and this gives you a more comprehensive coverage picture. You're now annotating many, many, many compounds, and you can even include novel chemicals unknown to even the industries themselves. They might be byproducts. They may have synthesized a compound that's actually different than what they thought they synthesized. And, of course, the industries often don't release lists of what they're producing. So, if anything, they're novel to the research community. We don't know what's out there. We haven't been provided all the information, but we can, as detectives, use non-targeted analysis to find out what all those chemicals are. And then from there on, we can do all of the health work. We can do legal, regulatory work, lawsuits, whatever needs to be done to protect us if those chemicals are toxic. There's no bias in our question, so we won't be missing random PFAS. We'll be getting everything that's covered by our instrument approach. We get a system-wide understanding. Now, major disadvantage of non-targeted analysis is that it's non-targeted. We don't have a known chemical standard, so our annotations, our identifications can be less confident than targeted analysis and generally are less confident. And so we have to be very careful when we're reporting chemicals that we've just discovered that haven't been discovered before, that we then follow up with a targeted approach. If this compound is very important and it's going to be brought down into regulation or something where there's going to be a lot of emphasis on this chemical compound, we then need to synthesize that chemical and do a targeted approach to get the exact amount of it and make sure that and validate what it is. So non-targeted is not quantitative, or at least usually not quantitative, and if it is, the error bars are much larger. You don't know as well what the concentration is, and you don't know as well whether you're right about the annotation. One additional thing about non-targeted analysis, in my view, is that it's fun. So target analysis, you run it, it's pretty robotic what you have to do. There is a lot of troubleshooting on the instrument and a lot of creative thinking there, but as far as the data is concerned, it's pretty simple. You're just looking for a peak, how much is there, so on and so forth. For the non-targeted analysis, again, we're using universal principles of chemical properties to try to understand what this new chemical is, and we have so many lines of evidence we can look at, and it's a big puzzle. And so all of the following tutorials will be looking at different pieces of that puzzle, how each one can provide information whether something is or isn't a PFAS, and even maybe this molecular formula, what atoms are in that PFAS, and maybe even what the structure of that PFAS is. And for that, we'll end this video tutorial, and I look forward to sharing with you in the next tutorials how to do non-targeted analysis.